Mm, Hello, everyone. Um okay, I will continue with the exercises. Now we are in the practice problem set 6, and I will do um, today the exercises 1 and 2. For these exercises, the first exercise, we have the mass M1 rest on the mass M2, which is connected to the ground here by a spring with the stiffness C. The system moves under the influence of the gravity. It's given the mass M1, the mass M2, the stiffness, spring stiffness C, and the gravity acceleration G. For the first question, we have to determine the force between the two masses M1 and M2 at this place here, both with the principle of D'Alembert and the law, the Newton law. The second question is, at which point does mass 1 lift off from the mass M2? That is means when it's lift off, that is means there is no contact between the mass M1 and M2. Okay, going now to the solution. Okay, what we have, we consider first the principle that we'll write here the, for the first question. E, here we write with D'Alembert. Principle Okay, with D'Alembert principle, what we have, as we know, we have to introduce the inertia forces. But it means we have here the sum of the forces, I, which is must be equal to 0. This is the principle of D'Alembert. But this means we have to look now which forces are between the two masses. Then we choose the coordinate system, let's say, with the position S, which is unidirectional. Here, what we have for the mass M1, there is the, let's say, inertia force or D'Alembert force, M1 multiplied by the acceleration, S dot dot. We have the weight, M1 multiplied by G, and we have the contact forces between the two masses, M1 and M2. Then in this case, we have also for M2, we have the mass M2 multiplied by G, which is the weight. We have also the D'Alembert force, or the inertia force, M2 multiplied by the acceleration. And we have here the spring force. Then it means if we do now the equilibrium, what we have here now the sum of the forces along uh, in S direction, which is here in our case in S direction, which is equal to 0. That is means we have minus we have minus M1 multiplied by S dot dot minus M1 G plus N equal to 0. Here, this one is only FH1, which means it's the inertia force due to the D'Alembert. That is means it's always against the motion, yeah, the direction of the axis S. Then it means here from this equation, we can get that the contact forces N, which is equal to M1 multiplied by G plus S dot dot. This is the first question. Now, if we look to here, the second mass, this is for, let's say, this is for M1. Now, if we look for the mass M2, they have the same principle. That is means here we have minus M2 multiplied by S2 S dot dot, sorry, S dot dot minus m2 multiplied by the acceleration, gravitational acceleration g minus spring force F Fa minus n equal to 0. Then we get here S dot dot, which is equal to minus m2 multiplied by g minus F, the feather force, Fa minus n, the contact force between the two masses, divided by m2. And this is here for the mass m2. Okay, now this is the D'Alembert inertia force here for the mass m1, and this one here is the inertia force of the mass 2. Okay, now what we have this first equation, this one, and we have the equation 2. Now we have the following, what we have here, this force FF2, FFA, the spring force, is only C multiplied by the position S. N is unknown, yeah, S is unknown, and we have S dot dot is also unknown. Then we have always two equations, yeah, with three unknowns. Now, if we apply now Newton, then what we have for Newton, we have the weight m1 g, we have the contact force n between the two masses, we have the weight m2 g for the mass m2, and we have the feather, the spring force FFA. Okay, now the same principle we have. If we take this, the motion, it's in this direction, yeah, then we have the coordinate system with S as for D'Alembert. In this case, if we write the equations, now we have here with, let's say, Newton, we have always the sum of the forces Fe, it's equal to the mass multiplied by the acceleration, EI. In our case, the acceleration is only s dot dot. Okay, it seems there is problem here. Then we have here. Then we set the Newton law. Then we have the sum of the forces, E, which is equal to the mass multiplied by the acceleration. Okay, now if we have the here, then if we have this system, as we said, that here we have the contact force N, the mass M1 multiplied by G, the same for the mass M2, with a feather force. In this case, if we are at the equilibrium, then we have here M1 S dot dot by the acceleration, which is equal to N minus M1 multiplied by G. Then in this case, we get here N, which is M1 multiplied by S dot dot plus G. And we have also for the mass M2 multiplied by S dot dot. This will be equal to minus N minus M2 multiplied by G minus the feather spring force FFA. And this here we get now, as for the lumbar, S dot dot will be equal to minus M2 G minus the force, spring force FFA, and minus the contact force N divided by M2. Okay, this will be now, as we said, 2 prime, and here will be 1 prime. They are the same equation as for the lumbar. Okay, now either for the next, to solve this exercise, we have only to choose either the lumbar or Newton. And now if we take the equation 2 in 1, then we get here, we replace N by its equation, we get here N will be equal to minus M1 divided by M1 plus M2, the feather, the spring force FFA. And this is equation for the contact force N, that we have only to replace S dot dot by this, in this equation here, S dot dot, and we get the expression for N. Okay. Now the question is to get the kinematic relation. Then we have to separate, let's say, 3 cases. There is the rest state, the static state, and the actual state due to the dynamic motion. Then it means if I can represent it here, this is now, we say here, we separate the things. This is initial state. That it means, yeah, at the at rest. Okay. Now, under the weight of the mass M1 and M2. Okay, there is here the displacement, the let's say the position. We take the reference here at the mass M2. Then there is displacement here. That is means at the displacement L0. That is there is a compression of the spring here, yeah, which will be comprised by this distance, let's say, or this position L0. And after this, there is the motion, okay, like vibration, let's say, which we take here the origin of the system here as, yeah, at the mass M2. This is now here, we call it static state. And this one is the actual state. That is means now, if we look at each state, what we have here, we cut at the spring position, let's say. Then we have at initial state, we have the spring force, which is equal to 0. Okay. Now, if we take the static state, that it means there is no dynamic motion or there is no motion. Yeah. In this case, we have here, as it's compressed, we have here the spring force. It's only the coefficient, spring coefficient C, multiplied by, yeah, the L0, which is the, let's say, the position, the new position, or, yeah, of the spring. This is L0, yeah. Of course, it's with minus as is under compression. And now, if we take the actual position here, the actual position, it's only now the spring force, is the static one plus, yeah, the C multiplied by S due to the dynamic motion, let's say. Okay, then it means now the position, if we take the reference at the mass M2, we have L0, we have compression, let's say, and after this, it moves up to with the position S, or yeah, with the position S. Okay. Now, if we take this equation, that it means we can write now here we can write that for this case here, for the static case that we have here, I write static state we have the force spring, which is equal to minus C multiplied by L0. And if we look to the equilibrium, here it's only minus the mass M1 plus M2 multiplied by G. Okay, then it means here, sorry, at static state, we have here the mass M2. Okay, then we have here, let's say, M2G, and we have also M1G. Okay, then this force is in equilibrium with this two forces or two weights. Here M1G and M2G. Then in this case, we have here minus M1 plus M2G as they are in the same direction. Okay, then it means here we can get, if we put this equation in here, then we get now in the expression of FA, that is means here we have actual state we have the spring force of FA which is equal to minus CL0 plus C multiplied by S. And this will give here now, as we have here minus CL0, it's only minus M1 plus M2 multiplied by G. Okay, then in this case, we will get here minus M1 plus M2 multiplied by G plus CS. Then if we now replace here this equation, okay, 5, this is 4. Then if we take here the 5, we replace it in this equation here, I call it 3. Then we will get here 5 in 3. Then we get here now the expression for N. N will be equal to M1 multiplied by G minus CS divided by M1 plus M2. This is the contact force between the two masses. Then in this case, that here we can get this equation now. This is the contact force. The second question is, to determine here at which point does mass M1 lift off from mass M2. In this case, that if it's lift off, that it means there is no contact. If there is no contact, then coming here to the second question, that it means here we can say N will be equal to 0. Yeah, this is the condition here that the mass M1 lift mass M2. In this case, if N is equal to 0, then it means we have to take this equation here. This will be equal to 0. Then it means M1 cannot be equal to 0. Then we have the second term here, which must be equal to 0. In this case, that we have now M1 multiplied by G minus CS divided by M1 plus M2 must be equal to 0. Then in this case, we have here S will be equal to M1 plus M2 divided by C multiplied by G. And this is it's only L0. This is the case where the mass M1 can lift off the mass M2. Okay, this is the position where it can be, it's only L0. Okay. Now, coming to the second exercise. Where we have here a wagon of mass capital letter M. This is a wagon here, which stand on a flat surface here. A mass M resting on the wagon with a small, let's say, small m, which is connected to it by a spring of stiffness C. Okay, at time t equal to 0, the mass m is released with the velocity v0, where b the spring is unstretched. Yeah. Then during the motion, there is no friction anywhere. Yeah. Between, let's say, the mass small m and the wagon, capital letter M, or the wheel with the ground. Okay. Which is given the mass of the wagon, small mass m, stiffness, and the velocity v0. What it's asked here to determine the system period of oscillation T, both with the D'Alembert principle and the theorem of conservation of momentum. Okay. Now we will start first with D'Alembert. Then we look first which forces are acting on the system here. I make exercise 2. That we look which forces are acting on the system, let's say. Okay. Then we take here D'Alembert. We know that the frequency, or here what we call in the exercises, yeah, that the period, okay, of oscillation, in this case, it's we have seen in the lecture, is defined by T, which is equal to 2 pi divided by omega, where we have here what we call differential equation, which is here S dot dot plus omega square multiplied by S equal to 0. This is the condition that here omega is given here, which is here the second term, okay, and the can be determined by this differential equation and the solution of this differential equation. And here we have the period or the frequency here, let's say the period, which is 2 pi divided by omega. Now, if we look to the system here, what we have, if we look to the contact between the small mass m and the wagon, capital letter M here, then what we have this small mass M. This is M at initial state, let's say, and we have here now the actual state, okay? This is now the initial state that the mass M move at this position here with, yeah, the position S, which has also the velocity S dot and the acceleration S dot dot, okay? Now what we have also, we have the velocity V, which is correspond to the absolute Y. We have the wagon, which move with the frame velocity, and the small m, which moves with the relative velocity, okay? Then it means the small m has frame velocity, which is the velocity of the wagon, and has also the relative velocity. Okay, the same for the acceleration. Okay, there is acceleration. We have seen that it's decomposed into three terms. Okay, the Coriolis, the frame one, and the relative one. Now, if we look here to the mass that has, if we make with D'Alembert, we have the inertia force here. I call it Ft of the mass small m, which is the mass m multiplied by the acceleration. As the motion is in this direction, okay, the inertia force is opposite to this direction. Also, we have the spring force Fa, which is equal to C, the coefficient multiplied by, yeah, the position S. Okay. Now, if I make the equilibrium, what we have here with D'Alembert, the sum of the forces Fe, it's equal to 0. Then in this case, what we have Ftm minus Fa is equal to 0. This is all what we have as forces, okay, in S direction. That it means we have here minus M E M absolute minus C S equal to 0. Okay, this is what we have as equation, and I noted it by 1. Okay, now if we look to the here, the S is unknown, of course. Yeah, the acceleration of the mass, absolute acceleration of the mass m here is also unknown. Then we have to determine it. Then we can write now that, let's say, S of the mass, sorry, S of the mass absolute here is equal to X plus S. Then it means we have here, we can also write that A absolute, the acceleration absolute here, it's only X dot dot plus S dot dot. Now, if I try to explain it now, okay, how it's come on, I take this picture here. we look now, this is what we call here static state. And here, actual state. That is means now we imagine, yeah, that we have here, yeah, the position of the gravity center of the whole system, the mass m, and the mass of the wagon, capital letter M. Okay, we take this position x, okay, of the gravity center here, okay, and now we imagine that there is distance b, okay, between the mass m and the gravity center, okay, or let's say center of mass. Now, if we look to the relative, this is here x, it's only when the wagon m moves, okay? We forget what it happens, yeah, on the wagon. That is means the wagon moves with x. This is what we call the frame, okay? And now, if we take during the actual state or during the motion, what we have also, we have the mass small letter m moves also on the wagon. And this is moves with, yeah, relative, uh, let's say it's relative motion, okay? Here, S, okay? Now, the whole system moves, the wagon moves, also small mass m, yeah, moves. Then in this case, what we look? We say, this is the new position, okay, of the gravity center now of the capital letter M, okay, SM. Now has moved with certain distance x, okay. This is the initial position, yeah, the static position, here B, the distance between the center of mass, yeah, of the wagon with the center of mass of the small um, or small um, mass m. Now then this is B, that is means it covered x. Now the rest here is only x minus b. Now when the mass m move to this position, I call it Sm, okay? Now this is the gravity center, the new position of the gravity center of uh, the small mass m. Then it will be here now the gravity center of the whole system, capital letter M, and small m will be S. And this has moved with, I call it Xi, okay? And this is will be the absolute one, okay? Which is decomposed now between, let's say, the mass small m will moves, okay? Which let's say here with the frame x and s, okay? Now, if we look now to the here, this one, then we can write here that if we replace now this M absolute by this, by its expression, which is x dot dot plus s dot dot. Okay, then we get here now this relation here minus s minus m x dot dot plus s dot dot. And this will be equal to 0. Okay. Now the both are unknown. Okay. Then we can see that here x is only here motion correspond to the position due to the motion of m, and this is, I call it frame, as here motion position due to the motion of small letter m, and this is here, it's the relative one, and here c here motion of m plus m. Okay, this is the total, the let's say the total or the global, let's say, motion of the system here, which is composed of small letter m, the mass small m, and the wagon with the capital letter M. Now, if we look now to the gravity center, we know that here we can write here center of mass we know that it's only here defined by, let's say, it's known that it's defined by C, which is here the sum. I write it by simplification, yeah. Let's say Y E M E divided by the sum of ME. That it means here, yeah, it's well known, this one. You should have seen it in static, yeah, and mechanics 1. Okay. Now, if I write what we have the mass M, okay? We have the mass M in our case, which is M1, let's say, for example, okay? In our case, we have here, I write for more and simplification, sorry. let's say y1 m1 plus y2 m2 m1 plus m2. In our case, m1 it's only capital letter M, m2 it's small letter m, okay, and y1 we have to define it. It's only the frame 1 x, okay, and y2 is the position to the between the distance here, yeah, as we have seen, it's only x minus b plus s. This is the new position, okay. This is sm, or let's say here we write it by y2, okay. For the sm here, the gravity center of the wagon here has moved with the distance x, okay. This is will be y1, yeah, and m1 is only m. Then it means we have here m multiplied by x and plus m multiplied by x minus b plus s divided by m plus capital letter M. Then if we develop further, then we get here the acceleration x dot dot. When we derive, it's only d second derivative with respect to time. And this is will be equal to, I write here, m plus capital letter M x dot dot plus m s dot dot divided by m plus capital letter M. And then c dot dot will be equal to x dot dot plus m divided m plus capital letter M s dot dot. This is, I write it by the equation 3. Now, if we look to this expression now, what we can say, we can say that here sorry. Then we have this third equation, okay? This is now for the position or the acceleration of the whole system. Okay, then it means now we can say that here, if we look now to the whole system, okay, what we have, then we have here this xi dot dot, okay, or let's say xi, which is the position of the gravity center of the whole system, okay, then it means here we have Sm, okay, which is this distance here, the gravity center of the mass, capital letter M, or the wagon here, and this is now Xi, okay. Now if we look here, what we have only the mass M, okay, capital letter M, the wagon, small m, okay, and the spring. Now what we see, okay, if we make now, this is the D'Alembert, okay, force. This is will be only D'Alembert force. I call it Ft, okay. Now what we have Ft, okay, which is equal to the mass m plus capital letter M multiplied by Xi dot dot with the principle of D'Alembert, it's equal to 0. Okay. In our case here, there is no other external forces. Okay. This can be internal forces of the spring can be considered if we have to cut here. Okay. But we let the system as it is. Okay. And we look what it happens. That it means here in our case, Xi dot dot will be equal to 0. Okay. Then it means here what we have, we will get here that let's say if we look to the expression of Xi dot dot, that it means here x dot dot plus m divided by small m capital letter M s dot dot will be equal to 0. Okay, following the expression of Xi dot dot here. Now, if we develop further, that is means here we have the expression of x dot dot, okay, then it means it's only here x dot dot is only minus small letter m plus capital letter M s dot dot. This is will be equal, sorry, there is the equality. Then this is the expression of the frame, let's say acceleration here, x dot dot, okay, as function of the relative acceleration. And we have here in the formula, okay, this is x dot dot plus s dot dot here, okay. Then if we replace now in this formula for the acceleration a dot absolute, then we have here, we get that minus cs minus m minus m divided by small letter m plus capital letter M s dot dot plus s dot dot. This is will be equal to 0. Okay. Then if we develop further, we will get s dot dot plus m plus capital letter M divided by capital letter M multiplied by C divided by small letter m multiplied by s equal to 0. Then we have here s dot dot plus 1 plus m divided by m multiplied by c divided by small letter m multiplied by s equal to 0. And now this is here, let's say, the differential equation. When you can see this term here, it's only omega square. Why? We have said that before, that we have the differential equation s dot dot plus omega square multiplied by s must be equal to 0. This is the differential equation. Yeah. And then we get here now this term here as omega square. Then it means here we can say that omega, it's only square root of 1 plus small letter m divided by capital letter M multiplied by C divided by small letter m. This is omega. That it means here we have t, which is the oscillation 2 pi divided by omega. Then it means here we get t, which is equal to 2 pi divided by 1 plus small letter m divided by capital letter M C, which divided by m. This is now the period of oscillation which is asked for. Okay, now if we take here, let's say the second case, okay, which is here asked first to find this period of oscillation T with D'Alembert. And now if we take the theorem of conservation of momentum, here conservation of momentum that's what we know. We know that the conservation of the momentum, that the sum here of the forces must be equal of the sum of the masses, yeah, multiplied by the velocity. Okay. In our case, if we took the Newton law, we have the mass multiplied by the total, or let's say the global acceleration, which is c dot dot. Okay. And in our case, that we have x dot dot plus s dot dot. Okay. Multiplied by small letter small mass m. Okay. Now, if we take here the definition, that here B, we note it in our lecture by the conservation of the momentum, that B at time t, okay, we have here two masses, m, which has the velocity x dot, which is the frame velocity, plus small m, which is here has the velocity frame plus relative s dot. Okay, and this is must be constant. For this, we say the conservation of momentum. That is means the momentum, there is no change in the momentum during the motion. Okay, we have here now B0, which correspond to, this is B at time t equal to 0. Okay, this is will be the mass m multiplied by the V0. Okay, as it said in the exercises, that the mass, yeah, here small letter m will be at time t0, the mass m is related with the velocity v0. Okay, this is only small, the mass small m. Now, if we develop further, that it means here what we get. Here now, if we make the time derivative t, I will write it down. We are at d b t, we make the time derivative of dt. This is will be b dot, okay, and it will be equal to the mass x dot dot plus m x dot dot plus s dot dot. This is equal one moment. One moment. Sorry. Okay. Sorry for this, let's say, technical problem. Then we have here, now if we make this derivative, as we have b dot here, it's equal the b dot. The b1, let's say it's this one, okay, and b0, let's say is this term here, must be equal to 0, okay. Then in this case here, what we have, the b dot Okay, the time derivative of B will be here, this part, and the second term here will be equal to 0, as the mass and V0 are constant. Okay, then in this case, we will get here x dot dot will be equal to minus m divided by m plus small letter m s dot dot. And this is the relationship between the frame and the uh, relative acceleration. Now, if we have this relation here, we can look now is the same as this one here, okay, which has been obtained by D'Alembert, okay. Now we have only to further develop, we get the following relation, and from this relation we get omega square, and from omega square we get the period of oscillation. Okay, I will stop now at this stage, and we will continue next time with the exercise 2 and the exercise, the exercise 3 and the exercise 4. Okay, bye.